This video examines VMC and zero sideslip using a Yaw Axis Simulator. With an engine out, VMC is the minimum airspeed that yaw effects can be balanced out, while zero sideslip provides the most efficient flight condition. In this video, we will look at a Yaw Axis Simulator, examine moments and centripetal force, define propeller effect and critical engine, cover the operational significance of zero sideslip, and ways of identifying a failed engine. Then we will explore VMC, including the factors that determine VMC. These include bank angle, density altitude, CG location, weight, critical versus non-critical engine, landing gear, and flaps. Finally, we will analyze dangerous situations and tools to avoid engine failure dangers. The Yaw Axis Simulator allows us to set various flight conditions and see their effects on the center picture. Variables can be changed on the upper left by typing new values and clicking on the labels to enter them. Other conditions can be set by clicking on the appropriate box. The center picture shows all horizontal forces that influence the rate of turn. For example, banking 5 degrees to the right creates a horizontal component of wing lift, causing a turn to the right. Similarly, applying 30 degrees right rudder deflection causes the fuselage to produce lift, also causing a turn to the right. The fuselage is an airfoil, which can be thought of as a wide symmetrical wing with a very short span turned on its side. Notice that the Yaw Axis Simulator has displays for moments and centripetal force. A moment about the center of gravity is defined as a force times the moment arm. The moment arm is the perpendicular distance from the center of gravity to the line of action of the force. In this picture, we see the moment arms for the thrust of the right engine and the lift produced by the vertical tail. Notice that the thrust produces a counterclockwise moment, while the tail lift produces a clockwise moment. If both moments are equal, the moment about the center of gravity is zero. Any moment about the center of gravity will cause an accelerating rotation about the CG. In order to maintain control, the moment about the CG must be zero, so that the rate of turn will be constant or zero. The moments shown in this picture are the major contributions, but there are other smaller ones as well. The Yaw Axis Simulator calculates all relevant values. We have just seen that a zero moment about the center of gravity produces a constant rate of turn. In order for the constant rate of turn to also be zero, all of the aerodynamic forces perpendicular to the direction of travel must cancel each other out. The combination of all of these perpendicular forces is known as the centripetal force. Therefore, in order for the rate of turn to be zero, both the moment about the CG and the centripetal force must be zero. This picture shows that a force perpendicular to the direction of travel causes the flight path direction to change. In order for the flight path direction to remain constant, this perpendicular force, the centripetal force, must be zero. Most prop airplanes have a critical engine. This is due to a phenomenon known as propeller effect. As angle of attack increases, the downward swinging blade produces more thrust than the upward swinging blade. This causes a left yawing moment when the engines rotate clockwise when viewed from the cockpit, which is the most common configuration. The net effect is that the total thrust is offset to the right of the engine centerline, as shown in the bottom picture. On the lower left of the Yaw Axis Simulator, we see three boxes that can select the engine orientation. For normal rotation, viewed clockwise from the cockpit, we see very little thrust shift at high speeds. If we now slow to a slower speed, we see a pronounced shift in the thrust vectors to the right. This makes the moment arm of the right engine larger, which produces a stronger yawing moment if the left engine were to fail. Therefore, the left engine is the critical engine. If these were jet engines, there would be no shift in the thrust vectors, and therefore no critical engine. Prop aircraft can avoid the critical engine by installing a counter-rotating right engine, which rotates counterclockwise when viewed from the cockpit. This makes the thrust of both engines have smaller and equal arms, and therefore no critical engine exists. In this video, both engines will have normal rotation, and the left engine will be the critical engine. Zero sideslip means that the sideslip angle must be zero. In other words, the longitudinal axis is aligned with the direction of travel. Drag is minimized when the sideslip angle is zero. This is especially important for engine-out situations where aircraft performance can be severely limited. Zero sideslip is an issue for engine failure situations because, unlike normal flight conditions, the ball indicator will not be centered when the sideslip angle is zero. We are now in a normal climb with both engines operating with the wings level. We will now fail the left engine. With no rudder pressure applied, the resulting sideslip angle causes the roll stability to begin a left roll, which requires right wheel deflection to maintain wings level. The large sideslip angle causes enough vertical tail lift to provide a zero moment about the CG. Feathering the left engine reduces the sideslip angle. The vertical tail lift provides a zero moment about the CG. But the fuselage lift, perpendicular thrust component, and vertical tail lift combine into the centripetal force that causes the left turn rate. Maintaining the wings level, we now apply right rudder pressure to stop the turn. Notice that to stop the turn by reducing the centripetal force to near zero, fuselage lift is necessary to cancel out the lift provided by the vertical tail. The ball is now centered, but the side slip angle is over 3 degrees. By reducing rudder pressure, the side slip angle can be reduced to 0. But the vertical tail lift is providing the centripetal force to cause a turn. We eliminate most of the centripetal force with a slight bank toward the operating engine. Horizontal wing lift now cancels the vertical tail lift. With slightly more than 2-degree bank angle toward the operating engine, we are able to maintain a 0 side slip angle. Note the right ball deflection. This is to be expected since when no turn is occurring, the ball sits in the lowest point in the raceway. This 2-degree bank angle is typical for light twin-engine airplanes. In visual conditions, yaw caused by a failed engine can be seen and immediately canceled by rudder pressure. However, in instrument conditions, this yaw is more difficult to detect. Therefore, we need another technique to identify the failed engine. This example shows engine failure identification for a jet aircraft. We will now fail the left engine. Note that we immediately apply right wheel pressure to cancel out the left roll caused by roll stability in response to the left yaw. Note that we now must apply rudder pressure in the direction of the downward side of the wheel. As we apply right rudder pressure, note that the control wheel position to maintain wings level returns to center as the side slip angle becomes 0. Now, since we are turning in this 0 side slip condition, we must establish slightly more than a 2-degree bank angle into the operating engine. We are now flying with a 0 side slip angle and a constant heading while holding right rudder pressure, therefore applying the dead foot dead engine rule. A dead left foot means a dead left engine. Engine failure identification for a prop aircraft may require a slight modification of the jet procedure. We will now fail the left engine and follow the jet procedure. Notice that in this case, a slight wheel pressure into the operating engine is required to maintain a zero sideslip angle. This is because prop-induced airflow over the right wing can increase lift on the right wing slightly more than the left, which requires slight right wheel pressure to maintain a zero bank angle. The significance of this effect can be measured by taping a yaw string to the nose and observing the wheel position when the sideslip angle is zero. Since this effect is typically small, the jet procedure for identifying the failed engine is just as effective for prop airplanes. The prior section on zero sideslip and failed engine determination referred to actions taken during normal flight. In this section on VMC, we are discussing a speed that must be avoided. We need to look at the factors that determine VMC so that we can remain safely above it. In this regard, VMC is much like stall speed. Let's find VMC using the Yaw Axis Simulator. We are in a normal climb and have failed the critical left engine. We will now apply enough right rudder to stop the turn. Notice that there is enough yaw into the operating engine to provide sufficient fuselage lift to cancel the tail lift and make the centripetal force zero. We will now slow down. As the airspeed decreases, additional right rudder pressure is necessary to maintain a constant heading. As the airspeed slowed from 90 knots to 83 knots, the necessary rudder deflection changed from 85% to 100%. We are now looking at a VMC of 83 knots with the wings level, and other conditions as shown, such as density, altitude, CG location, and weight. Bank angle has considerably more effect on VMC than any other variable. It can reduce VMC significantly, but it can also have some serious side effects. The tail force necessary to cancel all the moments about the center of gravity depend on three factors: shape of the vertical tail, which is changed by rudder position, airspeed, and sideslip angle, which determines the angle of attack on the vertical tail. In the previous video, we saw that rudder position maintained the necessary tail force as airspeed slowed. When the rudder position reaches 100%, any further reduction in airspeed will require an increase in tail angle of attack in order to maintain the necessary tail lift. In the following video, we will see that as airspeed is reduced, a slight yaw away from the operating engine increases the sideslip angle and tail angle of attack so that the necessary tail lift can be maintained. However, the change in sideslip angle changes fuselage lift, causing centripetal force and the resulting rate of turn. Banking into the operating engine can provide horizontal wing lift to reduce the centripetal force to zero. We can now see this bank angle effect in action. Beginning at VMC with the wings level, we now gradually reduce the airspeed. As the speed drops below VMC, a turn to the left begins. Banking into the operating engine reduces the centripetal force in order to stop the turn. Notice that at 78 knots, a 2-degree bank angle will stop the turn. Next, 77 knots and 2.6 degrees bank angle produce a zero rate of turn at the zero sideslip angle. .71 knots is the VMC value at 5 degrees bank angle. Increasing the bank angle to 7.4 degrees, we see that the VMC is now 65 knots. As the speed continues to slow, tail lift is maintained by increasing sideslip angle, and thereby increasing tail angle of attack and the vertical tail lift coefficient. At 100%, the vertical tail stalls, and further increases in the sideslip angle produce less tail lift. At 59 knots and 9 degrees bank angle, we see that this VMC value is very close to tail stall. A further reduction in airspeed causes the tail to stall, resulting in a large moment about the CG and an uncontrolled rate of turn. Density altitude reduces maximum thrust on the operating engine, and therefore has a significant effect on VMC. This effect is extremely important when doing VMC demonstrations. Beginning with a VMC value of 83 knots with wings level at sea level density, we will now find VMC at a density altitude of 8,000 feet. As rudder deflection hits 100%, we see that VMC at 8,000 feet is 74 knots with wings level. Let's repeat this sequence with a 5-degree bank angle. At sea level, we see that VMC is 71 knots. Changing density altitude to 8,000 feet. We now reduce airspeed. Notice that 100% rudder deflection maintains a constant heading at a VMC of 60 knots. Compared to sea level, a density altitude of 8,000 feet reduces VMC by about 10 knots for this airplane. The previous VMC effects, bank angle and density altitude, are large because they involve the primary causes of yaw, thrust, and vertical tail lift. The following effects are smaller because they involve smaller yaw contributions. First, let's look at the effects of CG location. Starting at VMC with the CG at 25% mean aerodynamic chord, the rear limit, we now move the CG to the forward limit, 0%. The resulting change in VMC is less than 1 knot for the wings level value of VMC. Changing to the VMC at 5 degrees bank angle and 0% mean aerodynamic chord, we select the rear limit of 25%. In this case, we find that VMC changes by only 1 knot. Now let's look at the effects of weight. When changing the weight from 6,000 pounds to 5,000 pounds, this video shows that the wings level VMC value does not change. Although weight affects the rate of heading change, it only affects the moment about the CG by its influence on the horizontal component of wing lift, which is 0 when the wings are level. Now, starting with the 73 knot VMC value at 5,000 pounds and 5 degrees bank angle, we change the weight to 6,000 pounds, and note the required rudder deflection is now less than 100%. Slowing down, we see the rudder deflection hits 100% again at the new VMC value of 71 knots. Remember that weight affects VMC only if the bank angle is not zero. At this point, let's compare the critical engine and non-critical engine VMC values. With the critical left engine failed, we see that the wings level VMC value is 83 knots. We will now fail the non-critical right engine. Note that the required rudder deflection is only 93%. Slowing down, we see the rudder deflection hits 100% at the new VMC value of 81 knots. Let's see how gear and flaps affect VMC. We will start with gear effects. A side slip angle causes a side force on the wheels and gear doors. The main gear forces are larger than the nose gear force, but the main gear is much closer to the CG, which makes the nose gear moment arm much greater than the main gear arm. Therefore, the resulting net moment is normally away from the operating engine for most airplanes, when the bank angle is greater than the typical zero side slip value of 2 to 3 degrees. This moment would increase VMC. At zero side slip, landing gear position has no effect on VMC since there are no side forces. The actual effect of gear extension on a particular airplane requires in-flight measurement. Now let's look at the effect of flaps. Compared to flaps up, a side slip angle normally causes slightly more drag on the relative wind side when flaps are extended. Therefore, the resulting net moment change is a small amount toward the operating engine, which decreases VMC, since less tail lift is required to balance the total moment about the CG. Like the landing gear case, at zero side slip, flap position has no effect on VMC. Also, flap position effect is minimal for bank angles near the typical zero side slip value of 2 to 3 degrees into the operating engine. Again, the actual effect of flap extension on a particular airplane requires in-flight measurement. We can now summarize all of the factors that affect VMC. These effects are typical for general aviation twin-engine airplanes. Note the large effect of bank angle, the moderate effect of density altitude, and the minimal effect of the other factors. The bank angle effect on VMC for typical general aviation twin-engine airplanes is between 2 and 3 knots per degree of bank angle. It is important to note that bank angle and high density altitudes can drive VMC to below stall speed. Let's see how these factors can lead to dangerous situations. In this example, the pilot operating handbook lists VMC as 73 knots, with no further information. Applying a common rule of thumb, we add 10% to find the minimum initial climb speed, which is 80 knots. We are now in an 80-knot climb with the wings level when the left engine fails. While maintaining a wings level attitude, we apply 100% right rudder deflection, but the turn rate continues. As we bank to the right to stop the turn, our distraction and poor climb performance allows the airspeed to deteriorate. Attempting to maintain heading with increasing bank angle and aileron pressure, we fail to notice the loss of airspeed. Finally, the left wing stalls with a large side slip angle, causing a loss of control and entry into a spin. So, what was the problem? The U.S. regulations for aircraft certification require that VMC not exceed a percentage of stall speed. This requirement is 20% for light airplanes and 13% for transports. Both light airplanes and transports are allowed to use up to a 5-degree bank angle to meet this requirement. Use of the full 5-degree bank angle to establish VMC is common practice. The stall speed for our simulated airplane is 61 knots. Maximum VMC is then 1.2 times 61 knots, which is 73 knots. Since the VMC value with the wings level is 83 knots, the full 5 degrees bank angle is required to bring the VMC value down to 73 knots. Now let's use the correct VMC to calculate our initial climb speed. We are now climbing at 91 knots, which is 10% above the wings level VMC of 83 knots. When the left engine fails, we apply right rudder pressure to stop the turn. Since we can now maintain heading with less than full rudder deflection, we can concentrate on maintaining airspeed without additional distractions, while reducing rudder pressure and establishing the zero side slip bank angle to maximize climb performance. VMC demonstrations have resulted in a number of fatal accidents. Let's see why this required training maneuver can be so hazardous. We have taken off from a sea-level airport and are now at 2,000 feet. After reducing the left engine to idle and setting takeoff power on the right engine, we raise the nose to gradually reduce airspeed while maintaining heading with increasing right rudder deflection. At full rudder deflection, we observe the heading begin to change. We would then recover by lowering the nose and reducing thrust on the right engine. Now let's repeat the VMC demonstration at a new location. We took off from an airport located at 3,000 feet and climbed to 5,000 feet, where the temperature was 84 degrees. Density altitude is 8,000 feet. Slowing down, we again maintain heading with increasing right rudder pressure. Before reaching full rudder deflection, the left wing stalls and a spin entry begins. What happened? We are apparently above our previously observed stall speed of 55 knots, but stalled before reaching full rudder deflection. The problem is that VMC is lower at high density altitudes, and indicated airspeed can be significantly inaccurate at high angles of attack. The correct stall speed in this case is 61 knots. EAS is equivalent airspeed, a combination of true airspeed and air density. An airspeed indicator with no errors would read equivalent airspeed. Corrected indicated airspeed is known as calibrated airspeed, which for practical purposes is the same as equivalent airspeed. Looking at the VMC change effects diagram, we see that two factors can lead to spin entry if airspeed is allowed to deteriorate into the stall region. These factors are maintaining heading with increasing bank angle after an engine failure, or maintaining heading with a moderate bank angle at high density altitude. Both of these factors cause large side slip angles that can create a spin entry when airspeed reaches stall speed. Let's look at some ways to avoid these dangerous situations. First, determine and use the wings level value of VMC as an airspeed reference. For example, be sure your initial climb speed is not less than 10% above VMC at zero bank angle. Next, no signs of decaying airspeed, such as increasing rudder pressure, bank angle, and control wheel deflection into the operating engine. Rudder pressure and control wheel deflection are the most significant, since small bank angle changes and airspeed indicator readings can go unnoticed under pressure. Let's look at the indications of decaying airspeed. Starting at 90 knots, the airspeed decrease begins. Maintaining wings level and a constant heading, increased rudder deflection is required as airspeed slows. After full rudder deflection, banking toward the operating engine is required to maintain heading. As the airspeed decrease continues, notice the increasing wheel deflection toward the operating engine. Approaching stall speed, observe the large wheel deflection versus the relatively small bank angle. During VMC demonstrations, it is extremely important to be aware of stall speed. While concentrating on heading and rudder pressure, lack of airspeed awareness at high density altitude can lead to a stall occurring with a large side slip angle, causing a spin entry. Remember that VMC demonstrations at a given indicated altitude that are safe at cold temperatures can be dangerous at hot temperatures. Finally, use the zero side slip bank angle when max performance is needed. Remember that safe operation with an engine out is all about airspeed. If you sense increasing rudder pressure or wheel or stick deflection toward the operating engine, push the nose down, even if it results in a descent. It is better to land under control almost any place rather than spin vertically into the ground.